Vice Chancellor for Research at the University of Missouri, where he's been for 2 years. Before then, he was here, and I should just give you a little bit of Rob's background. He grew up as a kid in Missouri, actually, and where he was an Eagle Scout and a member of MCSA. And he did do a little bit in science because he won the what was then the Westinghouse Science Fair Prize. I think you were #1 in the nation.
Oh, in the winners group.
In the winners group, right. So that's the Intel science thing today. And from there, he went to MIT as an undergrad and got a degree in physics. From there, got his PhD at the University of Santa Barbara in low-temperature physics under Gunther Allers.
Oh.
Then he was hired on at Sandia, I believe, as a member of the technical staff in 1989? 88.
Wow.
And he didn't stay there very long, though, before he realized that things were better at the University of New Mexico. And he started moonlighting over here almost immediately. And I think, did you come over here full-time at about 96?
96, right.
96, okay. So he was a professor in our department in 96. And you dabbled in some administration before you left here, and I'll let you explain that to people, but you started your administrative career probably about around 2002 or so. Yeah, something like that. And we are very excited to have you speak here today, Rob, on this topic, because ever since your appearance on 60 Minutes a year and a half ago, this department has been abuzz with discussions about cold fusion and so on.
Right?
Yeah, and
what happened in Missouri?
Yeah, so
That also didn't happen while I was here.
So when we asked Rob to speak, he put out a number of selections for titles, but we knew which one we wanted to hear, and we're grateful that you agreed to do so, to speak on this subject. So without further ado, Rob, on
Thanks, Andy, really. And thank you all. I mean, it's great to be back. It's wonderful to be here. I mean, wonderful place, UNM, and it's great to be here. Let me just say that I've taken a very different approach. I was just packing up to move to Missouri when I got called by a producer at 60 Minutes saying, would you read into some of the more recent papers on cold fusion? And I said, oh, come on, that's been debunked, right? I mean, it was just people fooling themselves, right? Well, that's what we thought too, but there have been these recent questions that have come up. So I agreed to read into the papers, and I did, and it kind of kept my mind active while I was more worried about packing up dishes and getting them, 1,000 miles across country. So, but in the process, I found that there is something very interesting here, and I'm certainly not an evangelist for cold fusion. I certainly won't say that there's any likelihood this is going to solve the world's energy problems or anything like that. I will say, from the standpoint of a scientist, there's something very interesting here. I don't know what it is, but I mean, that's the point where it's, I think, to me, pretty engaging. Feel free to stop me or challenge anything I say as we go through this. And what I thought I'd do is, first of all, start the long history of cold fusion. People don't realize, but it was September 17, 2006, that there was the first report of what looked to be a nuclear change from deuterium to helium that was reported in Germany in again, 1926. And there was some patent activity in Germany and Scandinavia later that year. There was a retraction to the paper that, well, if you're interested in seeing it, I'll show you. It's the question was whether the helium could be a contamination from the glass source, and that was still not resolved. So for that reason, the authors admitted that it could be from the source they had in control. They thought they ran control. They had done a control without hydrogen and palladium in their crucible, and over time saw that the helium lines did not appear the way they did when hydrogen was exposed to deuterium. So that was the first activity. It's interesting that there's been a lot of work on confirmed cold fusion and heavy hydrogen at near absolute zero, Russia, Berkeley, and other places, typically in the late 1950s. And this is catalyzed by naturally occurring muons. I thought I'd talk about that, not because that's necessarily what's going on here, but because it gives an example of how fusion process at low temperatures can be catalyzed. And then there was this fateful...
This is a well-known phenomenon.
Very well known, extremely well established. In fact,
both theoretically and experimentally.
Indeed. In fact, I'll be showing a little bit too of Jackson's paper that summarized this. And in fact, Alvarez at Berkeley, the drift chamber for studying things related to muon physics were, again, integral to the study in Berkeley of this approach of muon catalyzed fusion of hydrogen isotopes. Well, these reactions, without the muon catalyst, just these reactions are shown here. Two deuterons can form helium-3 and a neutron, proton and a triton. or helium-4 and a gamma, with the helium-4 and gamma being very, very rare, occurring only about 1 part per million, the other two reaction branches being about equally probable. D plus T can go to helium-4 and a neutron, again, and energy. The P plus D reaction is a very interesting one, because the P plus D reaction can go on this route, but if it's muon catalyzed, there can be another branch that puts very little energy into the helium-3 and a lot of energy into the muon after the catalyst occurs. But can palladium somehow catalyze its reactions in the solid state? I mean, the knee-jerk reaction of everyone seems that it's very unlikely. We're talking about a few electron volts of kinetic energy in processes in the solid state. How can that challenge, say, a barrier penetration at about 20 keV to bring two isotopes together to fuse? So it's very natural to think that they can't really be catalyzed in the solid state. But in condensed matter, certainly the muon catalyzes, and I thought I'd say a little bit about that physical process. And sorry, the screen size is a little bit off blanks. This is one of the best papers I've ever read. It's by J.D. Jackson, the same person who wrote the book on classical electrodynamics. Paper from April 15, 1957. And this is a summary of catalysis of nuclear reactions between hydrogen isotopes by mu meson. Just to kind of describe that for those who aren't familiar, the muon is 207 times more massive than the electron. It has a 2.2 microsecond half-life. And they shower the Earth at about 1 per square centimeter per minute. And they arrive at an average energy of about 3 GeV. So they come in highly relativistic. That's why we see them on the surface of the Earth. Famous special relativity demonstration experiment. Very few will come to rest in and around the D2 molecule, but if they collide correctly and the muon's left at near thermal velocities, it can form this d mu d, or muonated deuterium molecule, and it can form in a fraction of a microsecond at liquid deuterium densities. And then the D to D spacing goes down to a 1/200th, roughly, the spacing it had when it was just a normal D2 molecule. The vibrational energies go up to order of kilovolts, so now vibrational transitions emit soft X-rays. And the energies, kinetic energies that challenge the Coulomb barrier, are on the order of a kilovolt against a 20 kilovolt barrier. So now the probability for each vibrational close approach, provided you're in the S state, no rotation of the molecule, is about 10 to the minus 7, tunneling through the Coulomb barrier to create the fusion process. Remember, the vibrational period is 10 to the minus 17 seconds. So once this forms in a sigma state, a d mu d molecule, the fusion reaction will occur in very short order, and does. And all the necessary, or all the expected nuclear particles from that fusion are evident, as they would be if they were in free space. Well, each muon will catalyze about 10 D plus D fusion reactions before it combines with positively charged fission products or decays. It can catalyze about 100 D plus T fusions. There's a little bit difference. The D plus T is an asymmetric rotor. It loses its angular momentum faster to get to the sigma state. Other things that cause the catalysis to form are faster in the D plus T reaction, so more are typically catalyzed than the lifetime of the muon, or the sticking time of the nuclear ash. So this is cold fusion, but no energy technology impact, since muons are so expensive to create artificially, since their natural luminosity is far too low to really make this a viable form of energy. Now, if you look at the people that have considered the Coulomb barrier penetration problem, this one paper by Van Sicklin and Jones is an example. The probability that the vibrational modes of the D2 molecule in its sigma state at the standard temperature and pressure is about anywhere from 10 to the minus 70 to 10 to the minus 79 per second per D2 molecule. That means if you take all the D2 molecules on Earth, even throw in the D2O molecules in the ocean, and you ask yourself, okay, with that probability, how long would you have to wait to see a single fusion? It's about 10 to the 19th years. So the point is, you won't see D plus D fuse on just its own vibrational approach. But the muonated D2 molecule, well, again, it's 10 to the minus 7 probability for vibrational close approach, so this will occur, fairly immediately. It's also, I think, kind of a historical thing. This is a bit of an aside. But the muon was named after the mu meson, which was a mistake. The mu meson is a lepton. It's not hadronic. It's, it's a lepton. So this kind of, I think, points to a time when I. Rabi said, when people saw the muon show up, who ordered this? I mean, it came as a surprise, and I think certainly, all areas of sciences are ripe for potential surprise. Well, now cold fusion, but in the age of mass media. And this happened on March 22nd, 1989. I remember us at the March meeting in St. Louis. I remember everybody got really excited. Because of muon catalyzed fusion, people didn't discredit this immediately. They thought, hey, maybe there's something to this. You know, it's uncertain. By the way, if you'd like to come in, there's some space along the back, too. Well, so what happened was, in my opinion, that was a hideous media strategy. I've talked to Martin Fleischman. I've also talked to Chase Peterson, who was the president of the University of Utah at the time. Both gentlemen go like this. They say the idea that press conference was the other person's fault. And so I have no idea, you know, what pressure they may have received, or I have no idea, Chase Peterson claims that, they absolutely respect scientific freedom to make a decision what you say. So at any rate, big controversy, but in my opinion, a very bad media strategy, because they were claiming to have solved all the world's energy problems, possibly with the first appearance of something they found scientifically very interesting. This created, once people were unable to reproduce the effect, a very, very negative reaction in the physics community, especially in the U.S. And I will claim, and I'll go on to show in this talk why I think so, interesting science with possible engineering consequences suddenly became a pariah science. In fact, there's this great book by Michael Brooks called 13 Things That Don't Make Sense, and he says, speaking to a physics group about cold fusion is like trying to peddle pornography in church. And so it became kind of an area where people just wouldn't go there, just wouldn't even bring it up. And Martin Fleischman had two regrets. He mentioned that the 60 Minutes article that they ran in April 2009. And he had two regrets. First of all, he regretted calling it fusion because he saw an interesting effect and he didn't really know the physical origin. So he regretted having called it fusion in the first place. He also regretted that over-the-top news conference where they claimed that this solved the world's energy problems. And so it's interesting because I think, at least in retrospect, Martin Fleischman understands what went wrong and generally regrets it. But as Scott Pelley said at the same 60 Minutes thing, a strange thing happened on the way to oblivion. And that was about 200 excess heat results now have been seen, similar sometimes in scale, often similar in terms of what has been considered irreproducibility and variations that are uncontrolled, by many independent labs in many different countries from 1989 to 2009. And Ed Storms, who used to be at Los Alamos, has written a book called Low Energy Nuclear Reactions, which is how it's called primarily in the chemistry community, and in his book, and there have been more since that time. So people are seeing generally the same unusual scenarios we'll talk about in just a second. So what's different now from 1990, when some of the best experimentalists in the world were unable to reproduce the Fleischman and Ponds experiment? Now we know that you require a loading of deuterons to palladium that must exceed 0.88 for any excess heat to be observed. This is above the 0.77 limit of the beta phase of deuterated palladium. So it's very, very difficult to obtain these loadings. In fact, these loadings probably never exist in terms of they do never exist in terms of a static phase diagram of D on PD. In fact, this involves literally ramming in an overcharge of deuterium into the palladium. It's very hard to achieve. It's especially hard to achieve in electrochemical loading, the way Ponds and Fleischman did it. It's a little easier to achieve if you do a plasma-coupled D+ ion bombardment into the palladium. It's readily achieved in gas diffusion loading of nanoparticles or in co-deposition of palladium and deuterium. And as we'll see, the interesting thing is these excess heat effects are seen much more frequently, in fact, always in these gas diffusion loaded experiments, where achieving this level or much higher loading of D to PD is readily achievable. And let me show you the data from Michael McCoubre from SRI. These are his data. This shows excess power in watt per cubic centimeter. And again, does it scale with volume? Does it scale with area? We don't understand the mechanism. We don't know how it scales. But he just happened to plot watt per cubic centimeter of the sample against the atomic ratio D to PD of the loading. And as you see, it follows this somewhat parabolic curve, and this is a plot of, again, all the other excess heat reports that have occurred since 1989.
So each dot is an individual experiment?
Yes, each dot's the result.
From several labs?
Yeah. Of the 200 experiments, there are about 45 independent labs. So some of these dots are from the same lab. There's about 45 different labs around the world that have done, now I'm sure it's over 200 experiments on this, especially the interest in nanoparticles. We'll get to in a second. So this is the thing that seems to be missing. And again, even a talented person trying to do an electrochemical loading of D into PD would be hard pressed to get to a loading above 0.88. That's something we realize now. So that's a difference from what occurred back then. Now, the 60-minute story. After I had reviewed these papers, and again, I took kind of I'd say a generally hostile position when I started to review the papers, thinking this is probably not right. But then when I saw and talked to Mike McCoubre and a number of other people that were involved in it, I said, well, okay, well, it's kind of interesting. And then 60 Minutes asked if I'd go to see this company, Energetic Technologies, U.S.-owned company in Omer, Israel. And I agreed. And we did see this excess heat effect while I was there. I tried very hard to kind of tear into everything, like ground loops, like measurement errors that would be involved in the calorimetry and that sort of thing. And I didn't see any obvious problems. Now, there were 3 different cell designs, all very different, all reported excess heat at Omer, Israel. And 5 cells have reported excess heat exceeding a megajoule from a 0.3 gram palladium foil electrode. So to put this into perspective, we're talking maybe 2 millimoles of palladium here and a megajoule of total heat release over time. Now, chemical heat release you would have expected if this were, say, a PVD chemical reaction that was somehow delayed by the onset time that was often many hours, would have been maybe 100 to 800 joules. We'll talk a little bit more about that soon. Heat out to electrical energy in to accomplish the loading had been as high as 25, but rarely. 15, maybe 2 or 3 times a year. 8 was fairly common, and ratios on the order of 2 or 3 were seen on a monthly basis. So they didn't really know how to control the excess heat release. They didn't know how to control this kind of long delay time from the end of achieving the steady state loading and the onset of the excess heat. Again, a lot of control.
Those are magic numbers?
No.
Are they meant to represent a continuum or actual?
They're a continuum.
Okay.
They're a continuum. What I try to say is like they got 25 one time in the company's history in 2004, 15 maybe once a year, 8 maybe once a month, and 2 or 3 weekly. So that kind of gives a feel for how varied these results were. And there was no systematic understanding of what in the process made the difference. Okay, so still the experimental control is much less. It's not there really. It's still not understood. But what is understood is that before, where we would see maybe excess heat in 1 out of 10 or 11 samples normally prepared in the same way, they're seeing this now roughly half the time. Again, it varies from how you load. Now, quite similar results have been seen in labs in Italy, Russia, China, Germany, U.S., primarily SRI and the Navy labs at NRL and at Navy Spadewater, and I'll talk about those in a second. First, though, I thought it would be good to just talk about the 2 basic experiments, actually the 3 basic experiments they were doing, in 2 basic categories. And one was this concept of an isoparabolic calorimeter. All that really means is you have a near isothermal region separated by a high thermal insulator, a thermal resistor. So what you're doing is you're measuring T4 being substantially above T5, and the difference, T5 minus T4, divided by some effective conductivity, or resistivity I should say, is equal to the total heat flux shown in orange going outside of the calorimeter. So what you do typically is, even though there will be heat capacities and it takes some time to come to steady state, you let it come to steady state, hopefully, and once in steady state, you use this to infer the amount of heat out. So the output power will be proportional to this difference in the temperature. Now, it's interesting because there's another big concern, and that is during the process of the loading, electrochemically, you do water hydrolysis. So the hydrogen and oxygen comes up and recombines at a recombiner, a catalyst, drifts back down into the solution. The solution's about 0.1 millimole, or 0.1 molar butyrated lithium hydroxide. And so the situation is that there's another source of heat escape here. And the question is, how do you take that into account? Well, in the past, they've talked about some neutral potential, and they do an estimate of what that was. That could be a huge systematic effect. It could easily swamp what was being reported in the low excess heat results. But as it turns out, what they were doing was they were taking the potential difference V and the current I and not taking into account this heat that might be leaking out. So they were underestimating the excess heat from their reaction. Yes, Steve?
Why can't they put the recombiner into the gray box?
That's a great point. The Naval Research Lab wanted to do exactly that, to put all this inside the calorimetric boundary. So you have the whole thing under one boundary. And that makes a lot of sense. The problem is that if your catalyst isn't exactly right, the thing explodes.
Oh, not so good.
and so they gave it a try. The thing exploded. So the point is that the trick about a hydrogen-oxygen recombiner is the catalyst has to be near perfect, or you get into a situation where pressures build up of oxygen and hydrogen, and then something sparks it. So that's why they have this in a somewhat open system. But again, the Naval Research Lab has been trying to bring this catalyst, get the catalytic efficiency way up, and bring it into the calorimetric barrier. So you look at the whole thing in one way. Yes.
Is this electrochemical loading or?
This is electrochemical. Yeah, I should have said that. This would be the platinum electrodes as anodes and the palladium as cathode. Okay, and so it's the OD minus which is loading the deuterium into the cathode.
But I thought you said there was no excess heat with electrochemical loading.
Oh no, I'm sorry.
It's hard to get it.
It's hard to get it. Yeah, it's the hardest way to do it. But the point though is that all of these were the electrochemical loading case. Okay, and what I'll get to is that the hardest way around to do this is the electrochemical loading. The ion bombardment's a little easier.
Yeah.
But no, the interesting thing then is that another critical thing here is that you have to be careful not to accidentally average out the effect, meaning you want to digitize as quickly as possible to calculate what the actual output power is in any given time interval. So you can subtract I times V, the input power, and then sum up the excess heat over all time intervals delta T. And typically they were doing this with a digitization rate of about 40,000 times a second. Okay? And the question was, well, you could have something like, and this is something Richard Garland pointed out, electrolytic interrupter effect that could create an oscillation in the megahertz. So you could have a frequency component much, much higher than the measurement bandwidth of your apparatus that you'd simply miss. And so that's a very good point. They have looked at this with a 200 megahertz scope, though, and looked at the IV characteristics at 200 megahertz bandwidth, and then looked at whether they were correlated to give an unknown input power that was underestimated in the measurement bandwidth of 40 kilohertz.
Well, why couldn't they do an absolute input power measurement just by accumulation, heat, monitoring actual heat generation somewhere else that gave an actual power level?
Yeah, you could. I think that would be the experiment that, if I were reproducing the experiment that I'd like to do, would be to have either, it could be a dynamo, but better maybe a capacitor bank or something. And so you'd have a known energy storage in the capacitor bank, and so you'd be able to monitor the energy output from that bank into this loading of the experiment. And by doing that, you'd have an independent verification. But that has not been done. I agree, it would be worthwhile to do. But what they did was they looked at high bandwidth, and I'll address again. The other thing is this long onset and delay of the excess heat effect.
Right.
But,
well, I mean, I think the bandwidth, that was the Mississippi generator was the bandwidth problem. The guy who claimed he had perpetual motion.
Absolutely.
He was cheating on the bandwidth. So.
I've gotten a little bit into debunking here because there's a whole list of kind of common ways people fool themselves. And one is that they are in a certain measurement bandwidth and they have a power delivery at higher bandwidth that they don't take into account. And that certainly is a common. So that was checked for carefully here. I mean, obviously, before you go on television and say you think the excess of heat is real to 30 million people, you better be right, because that's an awful hard thing to go, oops, that's wrong. So the point, though, is that we were looking at these things in detail before I was ready to say anything at all. Really trying to see if there were common experimental inconsistencies. There's a different type of calorimeter that they used for their D+ plasma bombardment of the palladium layer. And the point is here what they're doing is their excess heat is again calorimetrically inferred, and I'll mention how it's different here in a flow calorimeter in a second. But what they're doing is they're accelerating the D+ ion into the palladium. So one thing, the D introduced into the palladium is coming in its plus state instead of minus state when it comes in as OD minus. And it's being loaded again by a potential difference of about 2,000 volts, accelerating the D+ ion to impact into the palladium itself. So it's ion remote plasma coupling that beds the ions in the palladium. So they did this as well. And this idea of a flow calorimeter is that you essentially control the temperature of the water flowing into your calorimeter, and then you look at the temperature rise of the temperature coming out. So it's T out minus T in that is multiplied by the heat capacity of the water in the flow stream and the flow rate to tell you what the power out of the calorimeter actually is. And so Pn, again, is the current of the D plus ions, hence the current in this electrical loop, times the voltage difference V. So that was how they were inferring the excess heat in these systems. And so again, the point here is that there are two different approaches, the flow calorimeter and also the ion bombardment instead of the electrochemical loading. Now, the interesting thing is that when you look at the different calorimeters, there's a whole different set of systematics to consider in doing the analysis of the experiments. The other thing that's interesting is that in the D plus plasma loading, they typically got excess heat about 1 time in 2, or it was more like 1 time in 4 or so when they were doing the electrochemical loading. At the time I saw their experiments in 2009. Actually, it was late 2008. The other interesting thing that's interesting about this is that I said there were 3 different techniques. This is one you saw before is one. The other technique is a variation of what we saw the first time. It's using this, but doing it in the field of very intense ultrasound. Doing the electrochemical loading in intense ultrasound, where the ultrasound ravages the surface. And in those cases, they saw excess heat about 70–80% of the time. And basically, the cavitation of the ultrasound, the electrolyte cavitates near the cathode, the palladium cathode, and really does great trauma to the cathode. Really disrupts the surface.
Is the intensity of the ultrasound high enough to cause nuclear reactions?
Gosh, I have no idea. I don't know for sure. I mean, I didn't really dig into that aspect of it, but they were reporting more likelihood of excess heat and higher excess heat in the cases where the cavitating electrolyte due to the ultrasound was occurring near the cathode. And I really didn't look at the possibility of there being any like sonoluminescent effect or something like that that might be at play. So I don't really know the answer to that. But now, this just shows where they put thermometers in many different locations to look for spurious thermal gradients. Again, T5 minus T4 is the important thing to look at. The interesting thing was, this is their Run 64 from 2004. This was a 25 times heat release that got everybody pretty excited. But what it went along and did was when this extreme heat release occurred, it went up to about 100 Celsius, at which point the electrolyte started to boil. And in fact, most of the electrolyte boiled away. And that stopped the apparent heat release. And in reporting the 25 to 1, they only considered it during the time that they were in the calibrated range of the apparatus. Once it started to boil the electrolyte and whistle the recombiner and make quite a scene, during those times they discredited any estimate of excess heat beyond that time because their calorimeter was out of calibration. But the interesting thing was then they were able to, I should go back and say, the one thing I thought was kind of interesting here is that during the time they had this really massive result. They had this whole thing in a lauda, which is like a refrigerated bath, and the excess heat from the system out of its calibration range was so intense it ruined the ability of the refrigerator to hold its bath temperature. So the bump you see in the bath temperature is due to the heat load of this experiment during this release. Now, they then looked at what the power output as a function of time was during this. Black is the power input, red is the power output, very jagged. And the power output maximum was about 34 watts, roughly. They integrate this to get the output energy. And they show the blue being the output energy of the system, the green being the input energy during the loading throughout the experiment, and black being the difference of the two, hence the excess energy. And so this, again, was this big result that got people pretty excited in 2004 with energetic technologies results. Overall, again, discrediting the data from the time when it was out of calibration because it was boiling its electrolyte, they reported 1.1 megajoule total output, 40 kilojoule input. And again, this was 2004, well before I ever heard of them. I certainly wasn't there to witness this myself, but I was looking over the data they showed me afterwards. So, is the excess heat effect real? Okay, and this kind of shows some of what I went through and some of the logic. First of all, for what I observed when I was there, recombiner concerns. Again, it ignores the recombiner heat leaked from the calorimeter. So the excess heat reports were underestimated by that leaked out. So there wasn't a systematic related to the recombiner, which is really what I thought the main driver would have been when I went there. I thought that's where the mistake would be. Volume chemical reaction. There was no evidence of any type of backflow of, say, oxygen or air or something that could create a volume chemical reaction with the electrolyte. It was not hermetically sealed, so there's no absolute assurance of that. But there were also no apparent results related to, say, an oxygen release that would have been, or an oxygen back diffusion that could have created a deep burn, a deuterium or hydrogen burn, where the hydrogen is being liberated at the cathode. How about ground loops or shorts? Isolation transformers were used throughout for the resistivity measurements of the palladium cathode, which is used to gauge its loading. And again, very good laboratory technique was observed. I mean, I didn't see any really shoddy laboratory practice from what you would expect to see in a laboratory doing careful measurements. Now, this underestimate of the input power, this electrolytic interrupter effect, okay? Again, it was about 40 kilohertz actual measurement system sampling, clearly greater than about a 20 kilohertz bandwidth, true bandwidth. Direct measurements with the scope showed no effect. In fact, if you just assume that what was probably antenna pickup on the scope was actually correlated and actually an electrolytic effect, then it would be like a 0.01% correction to the applied power that they thought they would apply. But again, it was generally uncorrelated antenna noise, so it was probably much, much less than that. And the calibrated physical source measurement that we just discussed would be a good thing to do, but it's not been done yet. I think that would be a very useful experiment to do. I would conclude, for this reason, the excess effect is very likely real. Okay, even if the input power is mismeasured to an electrolytic interrupter effect, why didn't it appear on the scope with much greater bandwidth? And what mechanism can store, say, 50 kilojoules to 4 megajoules of energy near a 0.3 gram, 2 millimole or so, palladium electrode for heat release a few hours or even a couple days later? Because this heat release that's seen occurs typically many hours to a couple days after the steady loading conditions have been achieved, for reasons, again, that aren't well understood. Now, even if some amazing new mechanism like this were to be discovered, it would be absent in other methods of systematic loading, but all those other methods also report excess heat. There is some excess heat we simply don't understand. Is it of fusion origin? Heck, I don't know. I mean, there's some data that would make a case one way or the other. But the point is, the fact that the excess heat is real and something that we can't put our hands on or figure out, to me as a scientist means it's interesting. Okay? So that's basically been what kind of attracted me to look into this further. Now, here's an argument for it being greater than chemical release. The energetic technologies cathode mass was, again, about 2 millimole. And the reaction, the enthalpy created by, or the heat of reaction for palladium reacting with deuterium is about 43 kilojoule per mole. So if 100, this could create maybe 100 joules of total excess heat if for some reason the palladium and deuterium hung out around the cathode and then agreed to react only, say, a few tens of hours later. And for the possibility of oxygen contamination coming in and reacting with the deuterium liberated at the cathode, then this reaction creates about 242 kilojoule per mole. So maybe 500 joules of delayed heat release that way. Again, if for some reason the reaction's delayed by hours from when the electric current that created the loading was applied. So many measurements show that this typical heat release on like something they saw every other day or so was about 50 kilojoules. Occasional heat releases of over a megajoule. And so the point is that there's something here that appears to be larger than what, at least to me, seems to be plausible heat releases given the very tiny size of the palladium foil. And it's usually from ambient temperature to about 100 C. with occasional reports of melting of the palladium electrode. But the point is that if this heat release is below 100 C, engineering-wise, it's not that consequential. I mean, you'd be looking for heat release at much higher temperatures to do gainful work. So again, let me stress, I see this as a scientific curiosity, not the salvation of our energy condition.
Did ET observe palladium melting?
They did not, because when they saw that the electrolyte was boiling, they started throwing in more electrolyte. So theirs did not melt. But there have been other groups that have reported melting of the foil. But again, very rarely, and no real controlled way to explore it afterwards. So again, what's going on? I don't know, and I think it's going to take a lot of controlled experiments to figure it out. Again, since the excess heat appears to be real, it's enough for me to kind of seriously be interested in it. Is it a nuclear fusion process? There have been hypotheses. All of them fall short, but there have been some interesting ideas. One is ignition through muon-catalyzed D plus D fusion near, but not in the palladium. Well, why would be palladium, deuterium, say, in voids? Because if the muon comes and gets anywhere close to a positive palladium atom inside the solid, K-shell replace, it'll fall into a bound state with the palladium atom and never be seen again, and not available for fusion. So if, in fact, this is muon catalysis going on in the heavily loaded palladium of deuterium, it's going to be in some void region before the muon gets basically trapped in the palladium ion. Another hypothesis, nanoscale structure of the palladium somehow catalyzes fusion. And there are some feasibility arguments to this that I think are pretty interesting, and I think would be worthwhile exploring. Evidence against the nuclear fusion process is very strong. There are no or very little nuclear particle emissions from the palladium chemical loading process. Now, there have been reports on ion bombardment and others of having fairly intense bursts of particles, including neutrons. But again, the systematic study of that is not yet complete, although a lot of people are interested in that today. And it's unclear how the system challenges its Coulomb behavior. Again, as I said at the very beginning, you're talking a few eV. How does that rival a 20 keV, say, Coulombic barrier? Evidence for a nuclear process. Well, there were these microcraters observed, and I thought it was interesting because Energetic Technologies, when I got there in December 2008, were really abuzz about these craters in their cathodes that appeared only after they'd seen extensive heat release. And they didn't see craters in the palladium cathodes that did not exhibit heat release. So they were very excited by that. And then I thought it was interesting, Navy Spey-War saw something similar in their coated positive electrodes, and neither group knew the other group had seen these things. But there's a big controversy over these microcraters I'll show you in a second. Many people think that they could be some type of chemical pitting, to which Spey-War and others have come back and done distribution and purity analysis to see if it looked like it was a thermal annealing that occurred near the crater, or whether it was something that might be, say, some chemical pitting. So this is a huge controversy right now and hasn't really worked its way out. The D plus D goes to helium-4 appears to be favored in these experiments of the electrochemical loading. With energy and momentum, they hypothesize, taken up by the lattice, since there's no gamma. But hey, that would be some very different method of the solid interacting in energy and momentum balance in a nuclear process. And that seems unlikely because nuclear processes occur in like 10 to the minus 17, 10 to the minus 18 seconds in attoseconds or so, whereas solids typically respond on the order of picoseconds. So it doesn't seem likely that the solid could really be involved in the energy and momentum balance. But there has been the proposition that this could be something quantum, like a Mossbauer-like process, but electromagnetic instead of in the phonons. When you do the probability of recoilless emission, assuming that this momentum from such a reaction is recoillessly taken up by the palladium matrix, you get a diminishingly small conventional Mossbauer probability. But the question is, could there be something more complex that we don't understand? And if you ask, could it be something you don't understand? I mean, it's like, well, by definition, I don't understand it, so I guess I have to be indifferent on the question. Other plausible quantum coherent mechanisms. There's a theorist at Purdue, Young Kim, who's proposed a BEC-like theory for deuterons inside compressed areas in the solid in voids. There have been other reports. Again, I'd say the Navy Spey-War report was one of the most interesting. The particle tracks in the CR39 plastic integrating detector. And helium-4 builds up in proportion to the excess heat. That's been established by a number of authors, but not in a hermetically sealed system. And the levels of excess heat reports are, as we talked before, well above chemical. Well, muon-catalyzed ignition, could it be this? Well, only low-energy muons can form the d mu d, as we said. The average thermal arrival rates are about 1 per square centimeter per hour in a one-story building, estimated by Cohen and Davies, in terms of the probability of a 3 GeV peak energy muon colliding fortuitously to end up in the deuterium at energies where it can do a molecular recombination. And again, it has to be in the d-rich void. Since it gets anywhere close to the PD, it will be it'll be muon K-shell captured, essentially 10 to the minus 12 meters from the nucleus, and trapped by the palladium and never available to form this d mu d muonated molecule that would then fuse. Let's see. It's interesting because this muon catalysis argument works out roughly right for describing the long onset times of the excess heat release, but it does not describe how the chain reaction is sustained, or why neutrons and tritium are absent, or why the gamma is absent if the D plus D goes to helium-4 plus gamma, which only occurs one time in a million of these reactions in free space, is somehow favored in the salt. So there are a lot of things that make the concept of the muon catalyzed ignition process being responsible for this suspect. Now, these are these images that got people pretty excited, energetic technologies. And these are these pits that they saw only in the cathodes that produced high excess heat results. And I asked if they had done any broad area survey to see the pitting and the size of the pitting and see if that correlates with the observed excess heat result. They had not done that work at the time. I believe they're trying to do that sort of thing now. But again, the origin of these microcraters are still under intense debate. But many people think from, again, results they do in impurity analysis, they claim that the distribution there versus the rolled palladium outside the region of the heat release suggests a thermal anneal. But again, a lot of controversy. It'll be interesting to see how that resolves. Again, about 4 months later, I was in, ironically, Utah for the American Chemical Society meeting. And there, Navy SPAWAR had grown their samples in a very different way. That's why the surface looks so different, using a co-deposition of palladium and deuterium. And there they were seeing these microcraters as well, and they were going through a similar analysis, thinking it might be evidence of the point-wise extreme heat release. Now, this group that's cited here, let's see, the Young Kim for corrections to this basic method, reapplying this method to the question of the crater formation. The question was, okay, how many D plus D fusion reactions would have to occur to create the heat release, again, under the electrolyte necessary to see this crater formation in the case of the work that was done at Energetic Technologies. It turns out to be about 200 million reactions to create enough heat, fusion reactions, to have this effect on the surface, if in fact that's the origin of these craters. Well, I think this is one thing that, at least to me, seems a lot more intriguing, and that's the possibility of palladium nanoparticle excess heat that's been observed now by a number of groups. These nanoparticles are less than 10 nanometer in diameter. In fact, the best results come from the results get more apparent as the nanoparticle gets smaller and smaller. And many of these results have been taken for 1 nanometer or smaller particles. And it's grown in a perovskite structure, these nanoparticles, we'll discuss in just a second. And the point is the nanoparticle size is much less than the hydrogen passivation layer thickness in palladium. So just by gas diffusion at ambient pressures, you can get a loading of like 1.1, and 0.88 seems to be necessary for any excess power observation. So this is the easy way to do it. And Arata, who came here in fact in 1997, he came to the University of New Mexico and gave a talk, and he was giving some talks on his earlier results on possible cold fusion. And I thought it was interesting. He's twice won the Emperor's Award in Japan. He's recognized as one of the top scientist engineers in Japan. And I listened to that and thought, wow, it was interesting. And then I was kind of warned, I think, and I appreciate the warning from Charles Beckel at the time. Well, watch out. This is so controversial. It's like flying into the bug zapper. And, so I appreciated his warning. But that was the first time I realized that there might be something here. Now, in terms of, it's what's right, not who's right, but there have been a number of outstanding scientists think there's something to this. There have been a number of outstanding scientists think there's nothing to this. So my opinion is that the opinions of people don't matter. It's the results of reproducible experiments that really count. But it's interesting that he did these results where he saw the excess heat from these palladium zirconium oxide perovskite composites. And this has been reported recently also by this group, Kitamura's group in Japan. And the NRL has also confirmed these results thousands of times and never once saw them not repeat in terms of these anomalous heat effects in the palladium particles. But the interesting thing is that the concern I have here is everybody's been using the same sample where the particles are grown in this perovskite structure. The perovskite structure has H2O as part of its chemical composition. And the excess heat seen here on the low end of the range, where they're kind of borderline at about as high as you'd expect to see chemical. So the point is, you can't rule out just by order of the heat release that it's not chemical. And there could be a chemical substitution that's giving rise to this excess heat after all. So it would be very interesting to produce these nanoparticles in a controlled experiment with no perovskite, repeat the experiments, and see that it's not an excess heat effect from a more chemical origin. But this quickly explains the experiment. I won't go over it in great detail. But it uses either H2 or D2 gas, H2 for the control, never sees an anomalous heat effect with H2. It's a it's a water flow calorimeter. So it's a raise in the water temperature that he uses to infer the excess heat. And in the measurements that he makes, he actually runs D2 and H2 side by side. So he has a control running on a separate mirror experiment to this one in the same lab with the same condition. By and large, there are some baseline stabilities on this calorimeter. So when you dig into the data that was reported, the calorimeter has times of kind of sudden upsets that aren't explained. But nonetheless, when it looks stable, it seems fairly stable. But with that said, it would be very interesting to do this with, say, some microcalorimeter to see really what's going on. Now, this is a busy slide, but let me start over here. First, he starts with palladium black, which is about 0.1 micrometer, 10 to the minus 7 meter diameter palladium spheres on average. And what's shown here, the pressure of D2 in blue, pressure of H2 in purple. Again, this isn't the same sample. There's one sample being used for D2, another sample being used for H2. And then what he's showing is the excess power seen from H2 and from the D2 experiments. Both show this blip, and this blip is what would be expected due to the surface heat of absorption of the hydrogen onto the palladium metal. Okay? And then after that saturates, it goes down to within experimental error of 0 on its calorimeter over the course of over 1,000 minutes. And the fact that this pressure loading goes up and saturates again is as expected. So here basically, this corresponds to about a 0.2 eV per atom heat of absorption loading on the palladium, about what it would be in a volt. This is absolutely no surprise. 300 mesh palladium black, these are much smaller particles. And in these particles, still statistically, there's close similarity between hydrogen and deuterium in terms of the heat of absorption. And both show no really characteristic excess power later on after they've been loaded. But if you, this corresponds to a size of about 10 nanometers per particle. Now you go to 1 nanometer per particle, okay, about 0.001 micrometer per particle in this PD zirconium nanoparticle process. And when you do, you see two things that are interesting. One, D2 shows a much higher loading of hydrogen onto the palladium than does H2. It's statistically different. And the size of this is huge compared to what you would see in whole hydrogen passivation of a palladium surface. It's up by a factor of 10. So you have a 10 times greater anomalous heat of absorption. You see an isotope effect between deuterium and hydrogen. Again, these are at near room temperature. And as time goes on, after some 500 minutes, you see the onset of an excess heat that persists for a number of hours. Again, kind of consistent with what Arata has seen. And these anomalous absorption effects have been seen, and the isotope effect have been seen time and time again in automated experiments by the Naval Research Labs. The last I talked to them, they'd gone over 10,000 cycles and never not seen it. So again, there's something interesting going on. What it is, I don't claim to know. Could there possibly be a catalyst of the palladium that makes D plus D fusion work? Okay, just for some assumptions. This 0.88 rule, let's assume that for loadings less than 0.88, there's no effective deuterium to participate in this whatever unknown process is going on. So we'll only consider deuterium on the sample that's above concentration of 0.88. And a typical value for these nanoparticles is about 0.25 watt output from a 1 millimole of D2 absorbed on the palladium. And assume that either excess D goes into a PD-D2 nanophase, or that the excess D densely loads metallic voids in these tiny little particles. You know, no idea what's going on. I've talked to a number of people that do neutron scattering. I think it would be very interesting to do some scattering on these samples to try to infer how the deuterium actually goes down. If this is fusion, then the probability of fusion that would describe these levels of excess heat would be about a fusion rate of 10 to the minus 22 per DD pair per second. Okay? And Gupta at an International Atomic Energy conference in Trieste in 1989 did a theoretical analysis. And basically, they saw to get to a probability of this occurring, the screening function in the metal would be critically important. It could make a 4 or 5 order of magnitude variation. And for molecular fusion process where it stayed D2, even with optimal screening that they would predict from the palladium, this would be 10 to the minus 33 per second, 11 orders of magnitude below what was observed. But then they talked about atomic fusion where the D atom fuses with the D atom. And that would be 6 times 10 to the minus 21 per second per their computational techniques. Not inconsistent with the possibility that it could be a fusion origin. Certainly not a proof, especially since things were so strongly dependent upon the screening function. Okay, can PDD2 form at high D-loading and small palladium structure dimensions? Nobody knows right now, to my knowledge. And why is palladium so special anyway? Well, I can answer at least that last question. Palladium is an interesting metal. This is where it falls in the periodic table. I'm sorry, this is small. Nickel, palladium, platinum. Now, nickel's ground state is always 4s2, 3d8. That's why it's slightly magnetic. Platinum is always 6s0, 5d10. That's why it's a Nobel metal. That's why it doesn't react very strongly. Palladium, fascinatingly, has the ground state of platinum, but it's easily switched between that ground state and the ground state of nickel. And the thing that switches it, among other things that has been observed, are magnetic impurities in the close proximity. This is called stellar enhancement, and it gives rise to, effectively, a much higher effective moment of the impurity in palladium than in other metals. That's seen again because it can effectively induce a magnetic moment in the palladium metal that surrounds it. And this has been critical for these high-resolution thermometers that Steve builds and I used to build. But at any rate, so there's the point I'm making here is that palladium is right on the edge anyway. And why would that be interesting? Well, in most calculations, people assume things are essentially steady state in their calculations. Fluctuations of charge would be really critical here. And as charge fluctuations occur, could that create, again, a dynamical enhancement in the probability of exceeding the Coulomb barrier? And again, the Gupta plus Gupta theory gives some guide that it's not completely out of the question. There could be some effect of a palladium catalyst. The PD-D2 nanocatalyst has not been verified. It's just speculation. So here's that summarized again. There's been a lot of speculation along this line by others. Again, why would this favor the D plus D goes to helium-4 plus gamma branch so severely, and why would the gamma not be seen as a single gamma? These still are outstanding questions. Because, I should have mentioned, all these measurements, including at Naval Research Labs, on the excess heat from the palladium nanoparticles, and the results that have been seen at Kobe, Japan, by Kitamura's group, not all of them have looked for particles being emitted. None of them have seen it. So the gas diffusion loading nanoparticles have not shown a particle emission like you'd expect to see. Interestingly enough, ion bombardment in palladium has. And there have been kind of occasional reports of there being particle emissions in other systems. So is it junk science, or is this interesting empirical data that should be investigated? Well, I'd say persistent observations like this excess heat, and incidentally, I've been talking to Mac Beasley at Stanford about this, superconductivity above room temperature that have been reported by a number of responsible groups but never easily reproduced, should be treated as empirical evidence that our understanding of the physics is incomplete. Okay? It's just that it's not to say that there's any engineering basis, you're not going to go design or create a new engineering technology on this, but you are to say, in my opinion, that enough people have seen these kind of very unusual reports that it's worth really close scrutiny. It's just too inconvenient scientifically or counterproductive to dismiss these observations, in my opinion, as junk science. And again, I put in a big plug for taking a dispassionate approach and just following the data. The scientific method is the only thing we've got. It's fortunately the only thing that will help us. And simply apply the scientific method over and over again without prejudice and see where the data leads you. So I would conclude excess heat effect is likely real. It merits serious study because I don't understand where it comes from. Just curiosity-driven research. I think probably a lot of work remains ahead to figure out what's going on. And the absorption and excess heat variation with palladium characteristic size has been established. Far more work's been done along the lines of what you saw in the Kitamura results. And they're an interesting systematic that is also not yet understood, but which reproduces all the time. And determine how the deuterium goes down on the palladium nanoparticles would be really interesting if there's a way to do that. Now for a hunch, and it's just a guess of sorts, but I am going to admit I'm holding out. I'm doing some work in this regard of looking for possible particle emissions of palladium. The initial results are fascinating. This area is plagued with initial results that don't reproduce. And I'm of the old school where I won't publish anything until I see that it reproduces somewhat. But I guess it's more personal preference. So we haven't published yet, but maybe soon. But there could be a warm fusion, possibly muon-assisted, process that results in particle emissions of as would be expected. Can the the metal environment change the muon ash binding rate? Because otherwise, 100 reactions would be virtually undetectable by any substantial sensor. Is there an economic pathway that is yet undiscovered to produce some type of muon source that would make, again, a persistence beyond like 100 fusions for the rare muon, or 10 fusions for the rare muon in the case of D plus D in the liquid state? So the point is that there's a possibility that there could be multiple processes going on. In fact, at this density of deuterium, with the muon flux we know there should be some muon catalyzed fusion if in fact the deuterons are at this density in voids in the metal. Both could be going on. So that's basically all I really have prepared to say, but I'm happy. Any other questions or thoughts or concerns? Yes, Bernie.
So has anyone put any of this apparatus into a muon beam?
Yeah, that's a great question. Not to my knowledge. It would be really interesting to take this thing that's sitting around after the loading's complete and you're waiting for this 10-hour or so onset of the excess heat and hit it with pulsing muons and see if that induces an excess heat effect.
There are lots of very high-intensity muon beams in the world, right? So
yeah.
It would be easy to test very quickly whether this has anything to do with muons or not.
I think that would be great.
Short of that, you can slow down cosmic ray muons to enhance the stopping rate.
Oh, yeah.
Put some light brakes above the
Sure,
apparatus.
put moderators around it. Yeah, absolutely. Yeah, there have been two things. Now, no one has done that experiment. We had talked about how neat it would be to do that. And I think that if there's any muon source that would entertain the likes of this sort of thing, I think it would be very easy to bring such an apparatus to the muon source to see.
Well, don't call it cold fusion in the proposal.
Okay.
Sorry.
Low energy nuclear reactions are the cheap tuxedo that the Chemical Society is coming for. But okay, sure. But then the other thing was there were experiments done in Italy, and in Nea, Italy, there have been some excess heat results reported by some of the top scientists there in past years. And I asked Franco, gosh, I'm forgetting his last name, close collaborator of David Goodstein's, Franco. I'm embarrassed I'm forgetting his name right now. But he saw the 600 kilojoule release on a Fleischman and Ponds like experiment in the mid-2000s, around, or like the late 1990s. And so there was a flurry of interest by ANEA, the National Energy Lab of Italy, to do a whole series of experiments. And in one, they put this in the bottom of a mine, so it would be well below the penetration distance for any cosmic flux of muons. And so, or actually, it's the pion production in the upper atmosphere that pays into the muon, creates the shower. But the thing was, I asked them, did you see any excess heat ever unset there? And they said, well, we're never looking for excess heat. They didn't have it in the calorimeter. They were looking at the sample with particle sensors. And they never saw the emission of particles. But then again, most of the deuterium-loaded palladium that's been done electrochemically, they have not seen them either. So it's essentially a kind of an indeterminate null result.
So people have looked for neutrons
Yes, yes.
and never seen any neutrons that would
Well,
take away the future
Or
energy.
in dry environments where it's ionic bombardment into a metal, there have been reports of neutrons. And again, it's an area I'm very interested in right now, but again, and I've seen some exciting things, but I don't want to say anything more definitive till we find out if this is a reproducible thing. Well, we can tell another scientist, do it this way, and we'll see the same thing. So there have been observations, I would say still anecdotally, because again, not reproducibly, of neutron and other possible particle emissions. Now, the published results on that are from Navy SPAY-WAR, where they've used the CR39 sensor to look at neutron emissions from deuterated palladium. And they have a series of pretty compelling things. Very quickly, CR39, your eyeglasses are made out of this plastic, okay? If you have a 100 micron thick slab and a neutron comes through, you have about a 0.1% chance of the neutron ever doing anything interesting in the plastic. Most pass straight on through. About 0.1% of the time they collide with something, and the charged particle that collided with creates a track that's very, very characteristic of a neutron-induced recoil event in the plastic. The problem is that these plastics, these little tiles, you have a statistically significant measurement only for total neutron exposure above about 10 millisieverts. And SPAY-WAR, other laboratories, have run controls, and they see a consistent effect above the controls, but they don't see the adequate statistics to be really, really conclusive yet, because they haven't had a total fluence of over 10 millisieverts incident on the detector. It'd be very interesting.
The neutrons from the real reaction are monoenergetic. In both cases, EV and ET. I mean, you can buy neutron generators after all that use these
Absolutely.
reactions.
Yeah.
So you detect them with a plastic simulator in time of flight to actually measure the energy.
Yeah.
Because you're looking for monoenergetic neutrons. So
True, true. Again, it's just a matter, again, of the fluence of how many neutrons you see coming from this thing. And it's been so low. The luminosity of the neutron flux has been so low.
If it's zero, that tells you something.
Well, if it's zero, yeah, if it's zero in terms of compared to your control for the environmental background, it means, okay, you don't see
I mean,
anything.
if it gives off a megajoule.
Howard has the problem solved.
I'm sure he has.
Howard, what was your question?
Well, I was curious about the palladium nanoparticles. Are they coated? How are they served up to the deuterium?
Yeah.
How is the deuterium brought together with the nanoparticles? What kind of phase?
Right.
Are there beams?
No, for the nanoparticles, it's just about a 10 psi overpressure of D2 or H2 for the control, D2 for the deuterium. And then it's just a gas loading at about a 10 psi overpressure.
Onto what?
Onto
nanoparticles.
Yeah, onto the nanoparticles, and unfortunately, the materials that are used in this, I forget what the company's name is in Japan that makes these things, but it's a proprietary process where they're using this perovskite structure to eventually result in nanoparticles. And so that's where I'm concerned about whether these excess heat effects are really dependent upon the perovskite substrate or the nanoparticle itself. And that's where I think it would be interesting. But I have a hard time understanding the origin of an isotope effect if it's truly a chemical origin. You know, at room temperature.
So the nanoparticles are not, you have these crystals sitting in a vessel, and you're putting deuterium under pressure.
Right.
And then you're saying, well, nanoparticles are being formed in this mixture?
Well, the nanoparticles are already formed in some prior process, and We've looked with them
Have you
electron
have
microscopy.
TEM measurements
Oh,
of
we do.
distributions, and so you have individual, are they stuck together, are they conglomerated?
Some are clustered, but many of them are independent. And I think it's this proprietary process that, again, the company that sells these materials won't go into
Pretty close
detail.
to an oxide-supported catalyst process, I would imagine. That's what
Probably
they like
something
to.
like
That's how they activate platinum
Oh.
and many things. They're trying to give them an oxide support
Yeah.
to get bare metal nanoparticles on the end.
Yeah,
Well,
exactly.
if it's a catalytic process, then the catalyst won't be used up, and so you would never have to replace these
Oh.
crystals, would you?
Well,
So you could just, once the cell has produced energy, you want to cool down or whatever, and you could use it
Right.
again. Can you use it again?
that's what the Navy's
Does
seen.
it
They've
reproduce?
cycled these time and time again, and they see a little decrease in the anomalous excess heat after 20, 30 cycles, but they see it cycles fairly dependably. And for the Naval Research Labs measurements. But getting back to the CR39, you clearly see something significant above the background pane of the CR39. There's also been work with moderated helium-3 sensors where you see what registers to be a very, very intense event of neutrons. But it appears that, again, it's a very, very fast pulse of a lot of neutrons. And again, that's why the integrated sensors like have been used by Spavor labs have been so useful. So it's clearly better than your control, but it's clearly not up to standards of adequate exposure to give proper statistics to infer from the CR39 that it's really what you think it is. So the thing would be to optimize the neutron flux from these things, like what Navy Spavor has seen some initial results in, up the neutron flux significantly, get 10, 20, 30 millisieverts of exposure on the pane, keep running your controls, of course, elsewhere in the lab, and then be able to do the statistics to make a proper claim of neutron flux and what their energy is. There's some energy that you can infer too from a statistical effect if you have adequate number of events in the CR39. But right now, it's on the order of maybe 700-800 microsieverts of total exposure on the plastic. It's much lower than what would be necessary to do a good statistical job with that as a sensor. Yes.
Do you have to go to CHTM soon?
Yeah. 2 o'clock.
So, is there another question?
And if I could catch a ride over.
So everybody else,
Want to write? I'll say.
everybody else can post their questions online.
Sure. Feel free to email me. It's an interesting system, and I'd say.
Just one quick, these folks who work on this, who funds them?
Do you wanna write
Are
something?
they
Right.
all private funding?
That's a very good point that Monsieur asked.
Oh, yeah, that's
Almost
right.
all of this is private funding, and there have been extensive private funding by certain companies that are really interested in this. To my knowledge, the only U.S. public funding has been a couple $1 million or so through the Naval Research Lab from one of the defense funding agencies. And so there's been very little public money. There's been significantly more public money funding this in both Japan and Italy. So, but the point is there's virtually no public funding. This is an unusual situation where private funding greatly outstrips the public funding in this area.
Interesting funding.
Yes, to the tune of maybe $2 million or so to Naval Research Labs for the measurements I just mentioned. To my knowledge, that's the only U.S. funded, publicly funded investigation by the United States in this.
Thank you, Ron.
Thank you.